So we've got the 2022 triple paper for Unit 2, and you can see the grade boundaries there and what's expected from each question as we go through. And then we've got the formula sheet. Straight into the first question then on radioactivity. So alpha, helium nucleus, beta, fast moving electron, gamma, high energy EM wave. You can see that the symbols are there. You're not asked for the symbols in this case, but be sure to add the mass numbers and the proton numbers. Then we've got a background given, 18 counts in 30 seconds, so we need to get that per second. So we need to divide 30 into 18 to get 0.6. And then 2 ways to improve measurements, so measure for longer and repeat. Expect to get that mark. Explain why the background radiation is much higher in some parts of the countries. Well, there's different types of rocks, which mean that there might be more radon in those parts of the country. On to question C then, you can see that we've got the source and then the detector, and in between the detector we'll stick an absorber, and that absorber could be paper or aluminium or even lead sometimes. So from this we can see now that source 1 was given a reading of 312, and then you stick paper in front of it and there's no difference, so there's no alpha present, okay, because it hasn't dropped. In fact, it's gone up by 1, but that's just a little anomaly there. And then you stick aluminium and no change either, so there's just going to be gamma. Okay, so I'm sure if they stick lead in front of that now, there's going to be a drop. And then you can see source 2, 389 at the start, stick paper, dropped straight away, so there's alpha present. And then you stick aluminium in front of it, dropped again. So in this one, just alpha and beta, because there's nothing left. So even if you was to stick lead there now, nothing's going to happen. So this displays that there. So that's that mark. And then it says, explain one change a teacher can make. Well, let's include lead just to confirm that gamma is emitted in that one there. Okay. On to the next question then, which is question 2. And this is on space and the stars. So we've got a bunch of information here. And then we've got 2 boxes. There is going to give you the 2 marks. Oh, yes, sir. So when I'm looking through these statements, I'm just checking the table to see if they're true. And I'm sure that when you check all this, without spending too long on it, that the 2 statements that I've chosen there is the correct ones. And again, you're just using information from the table. Pluto was once considered to be a planet. Well, it's got a really small mass, so that's why it's not considered now a planet. And I think this continues, yes. So Ceres is another dwarf planet. So we're going to have to estimate now, because it's found between, located in the asteroid belt, so it's found between Mars and Jupiter. So the distances between there, if you check the table, is anywhere between 1.53 and 5.19. So I said 3, I've just gone in the middle. And then concludes that rocky planets have the greatest mass. And again, I'm just checking the table here. So this is one of those questions where you can earn a lot of marks by no previous knowledge, really. So long as you're good at reading tables and picking out the information, you can get some marks from that. So we do agree there. On to the next question, question 3, nuclear fusion. So this is quite a difficult question to start off with, because it's giving you H there, and it says it's got 1 proton, 1 neutron. So by the side of there, you can just see that I've got a mass number now. Remember, mass number contains the number of protons and neutrons, and sometimes we call it the nucleon number in physics. And then you've got the atomic number, or the proton number, which just shows you how many protons I got. So a 2 and a 1 for H there, hydrogen. And then we've got tritium, which is 3 and 1. So it's got 2 protons now. 2 neutrons and 1 proton. So it's got 1 on the bottom and then those extra 2 there, which is why we're getting this equation. So it's just showing that equation there. So we've got deuterium with tritium, and then that's going to give us helium and a neutron. And then when we add these up, 5 plus 1, 2 plus 3, they're equal. 5 on top there. 2 on the bottom there, 2 on the bottom there, because it's plus 0 All right. Explain why nuclear fusion is difficult to achieve on Earth. Well, you need very high temperatures, high pressures, and it's really difficult to contain those temperatures and pressures. For 2 marks. 2 reasons why radioactive waste is difficult to store safely. Well, they've got really long half-lives, and so they're dangerous for a long period of time, and they're highly ionizing, not really good to humans, okay? Very dangerous, penetrating. Question 4 then is again on radioactivity, but this time it's dealing with half-life, and we've got this practical that we do in year 11 where we use dice to model radioactive decay, and the dice that we remove represents the decay occurring. So you can see now that the number of dice remaining on the throw, so you can see that on the second throw, they've removed 13, I think, 15 minus 3 is 13 dice, and then so on and so on and so on. And then we need to plot that as a graph, so you need the 3 marks from there. You're going to have to come up with your own scale, and you're going to plot them, and then you're going to do the curve for 3 marks, so 1 mark each there. And then you can see my intercept lines, because we're going to go on to questions now where it's asking us for what the half-life is. Use a graph to determine how many... right, so this one is a tricky one, and you can see I've crossed out the mark there because this is tricky. So I think I've gone to my graph and I've said there's 32 dice. Is that right? Yeah, so 32 there. You can see on the roll that they've given me. So originally there was 37 left. Okay, minus the 32, so that leaves us with 5, okay, on our second throw. So second throw, 37, third throw, 32, 37 minus 32, going to give us 5. That's how many dice was removed. Determine how many throws it took for the initial dice, so that basically a half-life is 5.2. Now, I know you can't have 5.2 throws, but we need to go to the degree of accuracy on the graph. And because the graph goes up in 0.1s, actually 0.2s here, we go to that level of accuracy, so 5.2. If the experiment was repeated with 1,000 dice, use your results to predict how many throws it would take. So now I'm just using 1,000 as a start. So then we're looking at 3 half-lives. So third throw, so 1, 2, 3, half in 1,000 to 500 to 250 to 125. Okay. So we know that it's 5.2 half-life, number of throws there. So for every 5.2 throws, it halves. So we know that that's going to be 5.2 throws, that's going to be 5.2 throws, that's going to be 5.2 throws, which is why I've done 5.2 times the 3 half-lives that it takes. 1, 2, 3. Okay. And then on to the next one. Decay is a random process, to explain why we need to use larger sample size. Because it's a random process, we can increase the confidence in the results, and it's going to smooth out that curve. It's going to smooth out the fluctuating data, so the crosses that we find about this. So generally, the more data you've got, the tighter this line becomes. And it's going to reduce the number of anomalies as well. How are we looking for time? 8 minutes. Okay. I reckon we can do this in under 15. Let's go for it. So the diagram shows the absorption spectrum. So explain what the dark lines, how they're formed. So dark lines are formed when atoms in the star's atmosphere absorb the light at particular wavelengths. So each one of these is representing an atom at that wavelength. And this represents, it's like a barcode for a particular element. There could be a couple of elements there. Many scientists believe that the universe began with the Big Bang. This one's a nice question for 4 marks. I've said there, I've circled the 4. So you've got cosmic microwave background radiation, which is CMBR, and you've got cosmological redshift. You can just call it redshift. What these show is that the Big Bang, supposed Big Bang, because this can be detected throughout the universe and in equal amounts uniformly, and that the redshift shows that the wavelengths are stretched. And that the further away the galaxy is, the faster it's moving from us. So that's how it proves the Big Bang theory. On to question 6 then. This is a mechanics question on SUVAT, or XVAT as we call it now. So we're looking at acceleration there, we're looking at a speed there, we're looking at a distance there, or displacement, I should say. So the big thing with this is knowing whether it's an initial speed or final velocity. So I should say initial velocity, and final velocity. Well, a car is traveling at initial velocity, so it's giving you there. So u is 15, and then it decelerates to a stop. So this is going to be u, but not that we need that. This is going to be 0, but not that we need that yet. Constant rate for distance of that at 20 meters. So I've got enough information there to... Oh, actually, it's asking. It's asking for v. Sorry, I got caught, carried away there. It's not coming to a stop at all, is it? It's asking for v. So if it's asking for v, I'm going to put the question mark there. Because it's not giving me a time, I'm going to put n by the time. So this is the formula I use because it hasn't got t. And then I can rearrange this formula by square rooting both sides. And then the answer comes out to be 9.22. Next question then, during the deceleration, the work done. So the energy on the driver reduces the kinetic energy from that to that over a distance of 20. So we use work done, force times distance. So we need to get the energy difference, first of all, which is 3,500 joules. And then we're going to rearrange this. You can see the work done, 3,500. We don't know the force, but we do know the distance. And when I rearrange that, it comes out to 175. Airbags are designed as a safety feature. Well, any safety feature is going to increase the distance or increase the time which energy is transferred, and therefore we're going to reduce the force. Okay, and that's the relationship there. Question 7 then, 6 marker on Newton's laws. You can see there's a fair bit going on here, so I'll just try and briefly go through my thinking. So it states, for 6 marks, state Newton's 3 laws, and then how do they apply to the skydiver. Well, first thing I've done is just named the laws, so I'm not going to go through that because we should know these off by heart by now. And if you need to learn them, you need to learn them. So when the skydiver first jumps out, initially it's just weight that's acting. So there's a resultant force downwards on the skydiver. So that's Newton's second law. So this is where there's going to be acceleration, F equals ma, right, on that bit. And then as he speeds up, the air resistance is going to start equaling. So you're going to have two balanced forces. And this is Newton's first law because it's going at terminal velocity, okay? When there's no external forces and it's either in a constant motion or it's stationary, all right? Providing there's no external forces. And we also call it inertia. And then Newton's third law is a little bit more tricky because now we have to deal with sort of Newton's third law pairs where you've got the skydiver, the force of the skydiver hitting the air particles is the same as the air particles hitting back on the skydiver. So we can talk about Newton's third law in terms of the air resistance there. Okay. Then we've got a graph, a velocity time graph, which they actually draw the tangent on this because they're looking for an instantaneous acceleration at 5 seconds, by the look of it. And then we're going to work that out over here. So I say the change in y over the change in x, or the change in velocity over the change in t. And these, this is where I've got my information from the graph because I'm taking the difference in y and putting it over the difference in x. Describe the acceleration changes. So it decreases to 0 at 15 meters per second. Sorry, did I just say that? 15 seconds, sorry. So 15 seconds is... So you can see that decreases. Describe the acceleration. Yes. Sorry, I thought it meant velocity then. So there's no acceleration at this point because it's constant velocity. And if something's constant velocity, there's no acceleration. It's not getting any faster. It's just going at the speed it's going. And then to get the distance, we use the area under the graph. So the area under the graph there, you can see is half times base times height. So half times 5 times 33, which is, so half times, so it just wants this bit by here, okay? And I think that's the end of that question. So coming up to 15 minutes. So we're going to be just over 15 minutes now. For question 8 is about momentum. So we've got a nice little definition there. Conservation of momentum. Total momentum before collision is the total momentum after, providing no external forces are acting on it. Then we've got to calculate the total momentum of the skateboarder after the and the ball before the collision. So we're looking at let's have a look. So he's holding it at this point. Oh no, hang on. So I just realised I've not completed this question by you. I've made not a mistake, but I didn't realise that it wants the ball as well. I just took, and I just see now that it's worth 4 marks. So what we need to do in this case is 35 times 2, because that's how we get momentum, right? It's the mass times the velocity. So I'm okay there, but I got this ball now moving in the other direction, so 0.45 times minus 10, and that's going to give us minus 4.5, so I need to now, my answer is actually wrong there, it's not 70, because 70 minus 4.5 is actually going to give me 65.5, so I'm just going to see if this will work and change that now. So that's going to be 65.5, because it's going to be 70 minus the 4.5. It's not going to be minus, but it's going to be 4.5, and that's going to give me that 65 there. Kilograms meter per second is your unit, because we're dealing with because we're timesing a kilogram, and we're timesing it by a meters per second. That's where we get the units from. So sorry about that. I thought I did it. And then the very last question, well, I'm glad, because I'm getting quite tired now. Use the equation from page 2 to calculate the velocity of the skateboarder after it catches a rugby ball. So we're just going to use pretty much the same equation here, where it's momentum, because we know momentum is conserved. Okay, it's before and after we should get the same momentum. So we can actually solve for V, so long as we know what's before, and which we do. So there's that 65.5, which we just worked out. And then that's going to equal, my after it is my 35.45. And then velocity, because now, you're probably wondering why it's 35.45. That's the combined mass of the skater and the ball when he's holding it. So he's got 35 plus your 0.45. But I do not know the new speed. So I've got a combined mass, but a speed, and then I start simplifying to get that to that, and then I rearrange for V to give me 1.85. So what was that worth? 2 marks. And then we're looking at the energy before and after. So how much? So Tom suggests that kinetic energy conserved in the collision. Explain by using calculations whether or not you agree. So I'm going to use kinetic energy equals half mv squared, and it's important we put that squared there. So I'm going to use pretty much the same figures now. My mass is 35 on the skater, and the speed is 2 squared, and then I'm going to do the ball. Remember the minus, okay, that's really important. And again, if I hopefully, it doesn't look like I've done that, does it? It looks like I've got, so I'm just going to check. I'm just going to press pause a minute. I just realised because it's squared, it removes the minus, which makes sense because energy, you can't really have negative energy anyway. So it comes out to be 92. So this is correct. And then after, I've just done it for my, so that's my skater, that's my ball, and then this is my skater and ball, the mass per there, and then the new speed that I calculated there to give me 60.66. And you can see that there is a difference in energy. So I've worked that difference out to be 31, and that's either lost as sound or heat. So I do disagree. It's not conserved, so energy is not conserved there. So we managed to get it around about 19 minutes, which is not too bad. I hope this video has been beneficial to you, and good luck with your exams.